At the beginning of chapter 21, I introduced you to the electric force two different ways. First of all, I showed you the electric force by charging by friction, and then secondly, charging by induction. Recall that demonstration involving charging by induction. I have here an electroscope, which consists of a conducting piece of metal that is surrounded by an insulating material. And then in this particular design, the conductor is actually split up into two sticks, and one of the sticks can rotate, for example, like so. And then what I do is I take this electroscope, I take the conducting piece of metal, and I place it in the presence of an external electric field. That external electric field is supplied by this charged rod. This then results in a polarization in the piece of metal as electrons flow in one direction or the other, and then ultimately the two sticks, if you will, here in this conductor, in this electroscope design, repel each other such that one of them rotates. That is, like so. Like this. So once again, recall this demonstration involving charging by induction. Now what we seek to understand, however, a little bit more carefully, exactly what is going on when you take a conducting piece of metal, or a conductor in general, and you place it in the presence of an electric field. All right, let me move this off to the side. Okay, a conductor placed in the presence of an external electric field. Okay, now I'm not going to draw anything nearly as complicated, however, as my electroscope. Instead, let's just treat the conducting piece of metal as a sphere to keep it easy. Okay, so here's a spherical conductor. Okay, and then let's just say that I turn on an external electric field. How that happens is unimportant, but let's say that an external electric field appears. So an external E appears, like so. So here are a couple of field lines, like so. Okay, now what happens in the piece of metal? Well, think of the piece of metal as basically a ball of electrons. That's the easiest way of picturing things. Electrons in metal are only very loosely bound to their parent atoms, so they can easily flow within the metal. Think of the electrons as being analogous to a gas for simplicity. So then therefore, very quickly, literally in the case of nanoseconds, what happens is that the electrons begin to move within the piece of metal. And they move such that later on, they lock themselves into an equilibrium position such that they can no longer move. This ultimately happens in a very short period of time. So in this particular case, if we think of, say, a positive charge here somewhere that is causing this external electric field, this then means that electrons within the piece of metal are going to get attracted in this direction. So the electrons then begin to pile up at the surface of the conductor like so. But then because electrons are flowing in this direction, let me say electrons flow, they then leave this area over here, thereby leaving it positively charged, like so. As I begin to draw this diagram, now you can see the beginnings of how the piece of metal starts to become polarized. So the conductor is becoming polarized. All of this is taking place in a very short period of time. Eventually, however, all the electrons will stop flowing, such that all the electrons are essentially locked in place. This then means that the net force being exerted upon the electrons is equal to 0. All the electrons are stationary, and then a situation referred to as electrostatic equilibrium is achieved. So eventually, electrostatic equilibrium is achieved. In other words, the electrons are now stationary. piece of metal is completely polarized. Okay, so then, therefore, once electrostatic equilibrium has been achieved, what does the net electric field in this entire region of space look like? Okay, now when I say net electric field, I'm not just talking about the external electric field that is supplied by the charged rod, for example. It also includes the electric fields associated with all of the individual electrons. So once again, this is the net electric field once electrostatic equilibrium has been achieved. So right here is my piece of metal. Okay, let me begin to draw the beginnings of the electric field lines far away from the metal, much like the diagram on the other board. That is like so. The question is, however, what is the net electric field inside the conductor? And what does the net electric field look like at the surface of the conductor? Well, first of all, inside the conductor. Once again, keep in mind that electrostatic equilibrium has been achieved. The electrons are all essentially locked in place and they don't move. So then therefore, what is the net force being exerted upon each individual electron? 0. Therefore, what is the net electric field interacting with each individual electron? 0. So then therefore, within the piece of metal, the net electric field is equal to 0 for that reason. So there's no electric field inside the metal. Think of it this way. If there was an electric field inside the metal, like on the previous board, then electrons would be flowing. But once electrostatic equilibrium has been achieved and the electrons are locked in place, this then means that the net electric field inside the conductor is equal to 0. Okay, now let me begin to draw the individual electrons themselves like so, here at the surface, like on the diagram above. And then this side here is positively charged, like so. Once again, the piece of metal here is polarized. But now what is happening at the surface of the metal? In other words, what does the net electric field look like at the surface? The net electric field at the surface has to be perpendicular to the surface itself. I'll explain why in just a moment, but for now, let me draw it. Like so. So notice how I'm drawing these net electric field lines here as they begin to interact with the surface of the metal. Notice that I'm drawing the net electric field lines here as being perpendicular to the surface of the metal. Okay, so why is that, however? Why must the net electric field be perpendicular to the surface? For the following reason. Let's say that I look at one of the surfaces here, the left-hand side, which is negatively charged, where all the electrons have piled up. Okay, so let's say that right here, for example, is that surface, like so. Right here are the individual electrons all piled up. Once again, they're locked in place, they're stationary, the net force being exerted upon them is equal to 0, and then down below, the net electric field is equal to 0. What about at the surface itself? Well, imagine what would happen if the electric field line at the surface was not perpendicular to the surface. For example, if it, say, looked like this. Well, if the electric field line looked like this and it wasn't perpendicular to the surface, this then means that that electric field line would have components. It would have, for example, a component like so on my diagram, and it would also have a component like so. Take a look at this component right here, and keep in mind that we're talking about the net electric field. So if this is a component associated with the net electric field, this then means that ultimately there's going to be an electric force exerted upon each individual electron such that they then begin to accelerate. But that's not the case. Once again, once electrostatic equilibrium has been achieved and the electrons don't move, This then means that the net force being exerted upon them is equal to 0. Therefore, the net electric field interacting with them is equal to 0. For this reason, the net electric field line cannot look like this at the surface. It must be perpendicular to the surface. So this cannot happen. Because if it did, there would be a net force exerted upon an electron at the surface. And that net force would specifically come from this component. So for that reason, this cannot happen. Once again, the net electric field must be perpendicular to the surface. Instead, in other words, it looks like this. So right here is the surface again, like so. Here in black are individual electrons, like so. And then right here is the net electric field line, perpendicular to the surface. This then results in the diagram on the lower board showing the net electric field when you place a spherical conductor in the presence of an external electric field. That is this diagram here. Now, initially, when we first introduced this topic, it's useful to think of the spherical conductor as a solid piece of metal. That's fine. But it actually doesn't matter if it's hollow or not. So for example, let's say that there's a cavity inside of this spherical conductor. That is like so. This then means that what we have here is what is referred to as a spherically conducting shell. Is the net electric field inside not just the spherical conducting shell, but the cavity equal to 0 once electrostatic equilibrium has been achieved? Yes. Now there may be induced charges at the inner surface like so of the conducting shell. We'll see that in a specific example a little bit later on with a, by the way, much more symmetrical configuration than this. But regardless, however, because once again electrostatic equilibrium has been achieved, the net electric field, not just inside the spherical conducting shell, but the cavity itself, is equal to 0. This then means that you could shield something electronically from outside influences by basically surrounding it by a conductor. That is, if you have, in this case, a spherically conducting shell, and you have a cavity inside, you can then place something inside like so that you want to have protected from outside electrical influences. This specific engineering concept that takes advantage of this situation is called a Faraday cage. A Faraday cage is basically a conductor of some sort with a hole inside, and you can then place something inside the conductor such the net electric field that is being influenced or exerted upon it, that is equal to 0. So you can electronically shield something in that manner. So you've experienced Faraday cages for yourselves a couple of different ways. For example, if you've ever been in an elevator, which is basically a metal box, have you ever noticed that your cell phone signal drops off? And the reason why is because you're inside of a Faraday cage. So then therefore the net electric field inside is always going to be equal to 0, regardless as to what is happening outside of the elevator with external electric fields. Another example that you may be familiar with here at school is, say, driving down Temescal Canyon Road down towards the beach. Have you ever noticed that there's a section of the canyon, a section of Temescal Canyon Road, maybe about 100 yards wide or so, where you will have your cell phone signal drop off? And the reason for that is because essentially the cliff sides of the canyon are high enough to begin to act as a Faraday cage. And then the conducting material would be minerals, for example, that make up the rocks inside the canyon walls. Another nice example of a Faraday cage that's local is the Mcclure Tunnel. Have you ever driven through that tunnel while talking on a cell phone and your cell phone signal drops off? The reason why is because the steel rebar inside of the tunnel itself, that's inside the cement that is, the steel rebar acts as a Faraday cage and blocks an electronic signal. Okay, at this point, I want you to go ahead and pause this video. Just go ahead and conclude this video. And the next thing that I want you to watch is my demonstration of a Faraday cage where I actually use my cell phone, and I do so by surrounding it by tinfoil.